Hi, welcome back to my class in number theory. For today, we will continue with the elementary divisibility properties, two of which we have stated and we have proven in the last lesson. But I will state again the first two of the divisibility properties as a review. The first of the elementary divisibility properties states that n divides n, where n here is understood to be an integer. And this property means that everything divides itself. Every integer divides itself, and later on you will see that 0 divides 0. That is, the only integer that divides 0 is itself. The second property is known as the transitivity property or transitive property for divisibility. The transitivity property or transitive property for divisibility states that if D divides N and N divides M, this implies that D divides M, where D, N, and M are integers. And the proof of this property, transitivity property, we have shown in the last lesson. Now I will state the third divisibility property known as the linearity property. The third divisibility property is known as the linearity property. And the linearity property states that if D divides N, where D and N are integers, and D divides M, where M is an integer, so the given here, D divides both the integers N and M. This implies that D divides AN plus BM, where A and B are also integers, and this is true. This conclusion of the linearity property is true for all integers A and B. And you take note that this expression AN plus BM is called the linear combination of the integers N and M. That is why this third property of divisibility is called the linearity property. because the linear combination of all linear combinations of integers n and m for all a and b, that linear combination is a multiple of d. That is, d divides the linear combination of n and m for all integers a and b. Now we will prove this linearity property, and again we will show that if d divides the linear combination of n and m, we should be able to find the integer such that an plus bm is equal to the product of the divisor d or the factor d and that integer. And for us to find that integer, we will use the given or the premise in this linearity property that d divides n, which means that there is an integer such that n is equal to the product of the divisor d and that integer. And also we will use the second given that d divides m, which means that there is an integer such that m is equal to the product of d and that integer. We now prove the linearity property. Again, to show that the conclusion of the linearity property is correct, that is, d divides an plus bm. To show that d divides an plus bm, we must show that there exists an integer k. We are looking for the integer k such that this number, this linear combination of integers n and m, an plus bm is equal to the divisor d and the integer k that we want to find. And we make use of these two given. D divides n we make use of the given to find to show that there is an integer k such that the linear combination of n and m, an plus bm, is equal to the divisor d times the integer k. And we make use of the two given. The first given, d divides n. We are given that d divides n by definition of divisibility. D divides n means there exists an integer k1 such that the integer n is equal to the product of the divisor d and the integer k1. We are sure that there is an integer k1. If you multiply that by d, the divisor d, the product is equal to the integer n. Also, we are given that d divides m. D divides m by definition of divisibility. D divides n means that there exists an integer which I denote by k2 such that the integer m or the number m, which is an integer, is equal to the product of the divisor d and the integer k2. And we will make use of this to show that this is true. There is an integer k such that this is true. Continue, we will make use of these two equations, and we will make use of the multiplication property of equality. I will multiply this equation m equals d k1 by any integer a. And I will multiply the second equation m equals d times k2 by an integer b, where b is any integer. By multiplication property of equality for any integers a and b, I multiply the first equation by a n is equal to a d k1. And the second equation I will multiply by b, which is an integer. Multiply the left hand side by b, we get bm. Bm is equal to bb k2. And these two equations are still true because the multiplication property of equality says that if you multiply both sides of an equation by the same constant, the equality remains true. And this equation, we multiply both sides by any integer a. So this an is still equal to a dk1. Similarly, we multiply both sides of this equation by the integer b, and by multiplication property of equality, if we multiply the left hand side by b, we get bm. That is still equal to if we multiply the right hand side by b, we get b dk2. Now we add these two equations. We add the left hand side and we add the right hand side. We add the left hand side, we get an plus bm. And we add the right hand sides of the two equation, abk1 plus bbk2. And you can see that at the right hand side of the equation, there is a common factor d. And we factor out the common factor d. If you factor out b from the first term, what is left in the first term is a k1. If you factor out b from the second term, what is left in the second term is bk2. Now we get an plus bm equals b times quantity, the sum of ak1 plus bk2. Now k1 and k2 are integers, and this k1 and k2 satisfy these two equations because we are given that d divides n. So there exists an integer k1, and this equation is also satisfied by k2 because we are given that D divides M, which means that there exists an integer K2 such that M equals DK2. But A is any integer. I said in the last lesson that all small letters would represent integers. So here A, K1, B, K2 are all integers. If K1 is an integer and A is an integer, then the product A K1 is an integer by closure property for multiplication of integers. So the product A K1 is an integer. In the second term, if K2 is an integer and B is any integer, the product of these two integers, B and K2, is again an integer by closure property of multiplication. Hence, the sum of AK1, which is an integer, and the integer BK2, the sum of these two integers is again an integer. And because the set of integers is closed under addition. The product of these two integers is an integer. The product of these two integers is an integer because the set of integers is closed under multiplication. And the sum of this integer and this integer is another integer because the set of integers is also closed under addition. Therefore, this sum is an integer. And you can see that an plus bm equals t times quantity ak1 plus bk2 is of this form. Thus, the integer k that we are looking for is the sum ak1 plus bk2. Now, I let this integer, the sum of this integer and this integer, be the integer k. K equals ak1 plus bk2. And this equation up is written as an plus bm equals bk. Thus, we have shown that there is an integer k, which is equal actually to the sum of the integers ak1 and bk2. ak1 is an integer because it is a product of two integers a and k1. b, k2 is an integer because it is a product of the integers b, k2. And the sum is an integer which will represent by k. Therefore, if this is k, we get b times k equals an plus bm. Again, we have shown that there is an integer k equal to this value such that an plus bm equals bk. Thus, we can conclude that B divides the linear combination of n and m. We therefore conclude that B divides the linear combination of n and m given by an plus bm for all integers a and b. We take the integers a and b as any integers. And B divides an plus bm because we have shown that there is an integer k which is equal to this such that this linear combination of n and m, an plus bm, is equal to the divisor d times the integer k, which is equal to ak1 plus bk2. And that completes the proof of the linearity property. and we indicate the end of proof by this shaded rectangle. We now state the fourth property, the fourth divisibility property known as the multiplication property. We now state the fourth property of divisibility, and it's called the multiplication property. If d divides n, where d and n are integers, this implies that AD divides AN. You can see that the integer d is multiplied by a, and the integer n is multiplied by a. And that is why this is called the multiplication property of divisibility. Now we prove. We start with the premise and the given that d divides n, and from there we show that AD divides AN. By definition of divisibility, d divides n means that there exists an integer, which I will denote by k, such that the number n is equal to d times that integer k. This is by definition of divisibility. The integer d, also known as divisor or factor of n, divides n, means that there exists an integer which I denoted by k, such that the integer n or the number n is equal to d times the integer k. Now, this property is true for any integer a. We multiply both sides of this equation by the integer a, and the equality will still be true because that is the property, the multiplication property of equality. If you multiply both sides of an equation by the same constant, the equality holds true. Again, by multiplication property of equality, if we multiply both sides of this equation by the integer a, the equality will still be true. We multiply the left-hand side by a, we get an, equals, we multiply the right-hand side dk by a. And the equality is still true for all integer a. Now, the right-hand side of this equation can be written as quantity AD multiplied by K by associative property of multiplication that is satisfied by the set of integers. By associative property of multiplication that is satisfied by the set of integers z, the product a times quantity dk is the same as the product of quantity AB and K. In this equation at the right hand side, we have the grouping of dk, and in this equation at the right hand side, we first multiply A and B, and the product we multiply by K. But the associative property says that regardless of the grouping, the product is the same. But we have to write the right hand side in this way to conform with the definition of divisibility. Now from this equation, we can conclude that AD divides the product AN because there is an integer K. Integer K exists such that the product AN is equal to the divisor AD and the integer K. Our conclusion, therefore, is the conclusion of the multiplication property of divisibility. AD divides AN because we have shown that there is an integer K that exists such that the number AN or the product AN is equal to the divisor AD times the integer K. And this completes the proof of the multiplication property of divisibility. Next, we state the cancellation property of divisibility. The cancellation property of divisibility states that if AD divides AN and the integer A is not equal to 0, this implies that D divides N. And this is known as the cancellation property of divisibility, because the integer A, which is not equal to 0, was cancelled from this statement AD divides by N. Again, we prove this property, cancellation property, and we start from the premise or the given that AD divides AN. Beginning from the given that AD divides AN, we make use of the definition of divisibility. And the definition of divisibility says that if AD divides AN, it means that there exists an integer K such that this number AN or the product AN is equal to the divisor AD multiplied by the integer K. This is by definition of divisibility. Now, since the integer A is not equal to 0, we can divide both sides of this equation by A, which is not equal to 0. And the equality will still be true by division property of equality. Again, by division property of equality, by division. By division property of equality, we divide both sides of this equation by a. And we can do that because a is not equal to 0. If a is 0, we cannot divide both sides of this equation by 0 because you know that division by 0 is not defined. But here a is not equal to 0, that is given. So we can divide both sides of this equation by a. Thus, an equals ad multiplied by k implies we divide the left hand side an by a equals we divide the right hand side ad multiplied by k by a. And a will cancel out from the left, you get n. A will cancel out from the right hand side and you get dk. And this implies that we have written the number n as the product of the divisor d and the integer k, which we are sure exists because from the given there exists an integer k, such that an is equal to ad multiplied by k. Hence, from this equation, we can conclude that d divides n because there exists an integer k such that the number n is equal to the product of the divisor d and the integer k. We therefore conclude that the number d divides n because from here we have shown that the number n is equal to the product of the divisor d and the integer k, which we are sure exists. And this completes the proof of the cancellation property of divisibility. We now state the next property, divisibility, the next divisibility property. Now state the next two properties of divisibility. The sixth property says that the integer 1 divides n. That means 1 is a divisor of every integer, or that is 1 is a factor of every integer. The seventh property says that if n divides 1, this implies that n is either equal to 1 or n is equal to negative 1. And we now prove the sixth divisibility property. Again, we start with the given 1 divides n. By definition of divisibility, the given that n divides 1 divides n, that is the given. Again, by definition of divisibility, the premise or given that 1 divides n means that there exists an integer k such that the number n is equal to the divisor 1 multiplied by the integer k. N equals 1 times the integer k, but 1 times the integer k is equal to k. and that's by property of the identity element for multiplication, which is 1. The identity element for multiplication is 1. If you multiply 1 by any integer k, the answer is the integer k. Now here n is given because we are given that 1 divides n for any integer n. So n here is given and n is equal to k. Thus we have shown that k exists and k is equal to the number n itself. Therefore we can conclude that 1 divides n because there is an integer k, and that integer k is equal to the number n or integer n itself. We therefore conclude that 1 divides n since we have shown that there exists an integer k which is equal to n such that n is equal to 1 times 1, the divisor 1 times the integer k which is equal to n. So 1 times k is equal to 1 times n, and 1 times n by property of the identity element for multiplication, 1 times n is equal to n. Therefore, this equation is satisfied. N times 1 equals k is satisfied. And it's equal to n. Now we prove the seventh property. Don't forget to write the shaded rectangle at the end of proof to indicate the end of proof. We now prove the seventh property of divisibility that states that if an integer n divides 1, then the integer n should be equal to 1 or negative 1. That is, the only integers that can divide 1 is 1 or negative 1. With the premise again, or the given in the property, the given is n divides 1, and you make use of the definition of divisibility. By definition of divisibility, the given that n divides 1 means that there exists an integer k. And with the property that the number 1 is equal to the product of the divisor n and the integer k. Now from this equation we have 1 equals nk. We divide both sides of this equation by n. And the equality will still be true by division property of equality. We divide 1 by n, and we divide nk by n. And from the right hand side, n will cancel out, and you simply k equals 1 over n. K equals 1 over n. So the integer k is equal to the reciprocal of n. And k must be an integer. K must be an integer. Now we consider values of n that will make 1 over n an integer. If n is equal to 0, we cannot do that because we cannot divide by 0. Although later on we will show that 0, the only number that divides 0 is 0. That is 0 divides itself. But 0 over 0 is indeterminate form. But here n cannot be 0 because 1 over 0 is undefined. But if you assign integers to n such as 2, 3, or greater than 2, any integers from 2, 1 over n will not be an integer. It will be a fraction. Proper fraction. Similarly, if you assign values of n that are negative, from negative 2 or less than negative 2, that is negative 2, if n is negative 2, negative 3, negative 4, etc., 1 over n is not an integer, but a negative proper fraction. Example, 1 over negative 2, 1 over negative 3. If the integer n is positive integer equal to 2 or greater than 2, then 1 over n is also not an integer. Example, 1 over 2, 1 over 3, 1 over 4, and so on. But if n is equal to 1, 1 divided by 1 is 1, which is an integer. So k is equal to 1 if n is 1 and 1 is an integer. Also, if n is equal to negative 1, 1 divided by negative 1 is negative 1, and that is the value of k. Negative 1 if n is negative 1. Thus, the only values of n that will make 1 over n an integer, which is the integer k we are looking for, is 1 or negative 1. The only way for this fraction 1 over n to be an integer is when n is 1 or when is negative 1. Thus, k will only be an integer if n is 1 equals 1 or n equals negative 1. Therefore, we conclude that 1 divides n implies that n is equal to 1 or n is equal to negative 1. Or we can write this as one expression: n divides n implies n equals plus or minus 1. That is, n either equals positive 1 or n equals negative 1. And that completes the proof of the 6th and 7th divisibility properties. We now state the 8th and the 9th divisibility properties. The 8th divisibility property says that d divides 0, which means that every integer divides 0, including 0, as we will show in the 9th divisibility property. That is, every integer is a factor of 0, or everything divides 0. Every integer divides 0. The 9th property says if 0 divides n, this implies that n equals 0, which means that only 0 is the only integer that divides 0, or 0 divides itself, although 0 over 0 is indeterminate. 0 over 0 is an example of indeterminate form, but we will show now that 0 divides 0, except that the value of 0 over 0 is indeterminate. We now prove the 8th divisibility property: d divides 0. Every integer divides 0. Again, we always start with the premise or the given that d divides 0. And we use the definition of divisibility. By definition of divisibility, the given that d divides 0 means that there exists an integer k such that the integer 0 is equal to the divisor k times the integer k that we are sure exists. And we start from this equation. We divide both sides of this equation by d. We start from this equation, 0 equals dk. We divide the left hand side by d, 0 divided by d, We divide the right hand side by d, dk, divide by d, and the equality will still be true because that is the division property of equality. Now, 0 divided by an integer d is equal to 0. Equals the right hand side d over d is 1, or d will cancel out from the right hand side, and the right hand side simplifies to k. Thus, the integer k is equal to 0, and 0 is an integer. Thus, k is equal to 0, and 0 is an integer. Therefore, this equation will be satisfied. 0 equals d times k, where the integer k is 0 and d is any integer, negative, 0, or positive. Therefore, we have shown that the integer k exists such that 0, the integer k exists and k is 0, such that 0 is equal to d times k. Therefore, we conclude that d divides 0. That is, every integer divides 0. That is, every integer d is a divisor of 0. Or we say that every integer is a factor of 0. We therefore conclude that d divides 0 because we have shown that there is an integer k, and that for the integer k equals 0, the number 0 is equal to the product of the divisor d and k, which is 0, and d is any integer. And that completes the proof of the 8th divisibility property. We now prove the 9th divisibility property. If 0 divides n, then n must be 0, which means that 0 is the only integer that divides 0, or 0 divides only 0. Start with the given in the 9th divisibility property that says 0 divides n. And by definition of divisibility, 0 divides n means that there exists an integer k. There exists an integer k such that the number n is equal to 0 times the integer k, or n equals 0 multiplied by k. And we start from this equation, n equals 0 times k. We have n equals 0 times k is equal to 0 for every integer k. Thus, we are sure that an integer k exists, and it can actually be any. K can be any of the integers. K can be negative integer, k can be 0 integer, or k can be positive integer. Or for all integers k, for any integer k, for every integer k, 0 times k will be 0. But 0 times k is equal to the value of n. So n is equal to 0 for every integer k. Therefore, we conclude that 0 divides n implies that n is equal to 0. And if n is equal to 0, we would have 0 divides 0, which means that 0 is the only number that divides 0, or 0 divides only 0. We can say that 0 divides 0 as we have proven in this property, but again, 0 over 0, or 0 divide by 0 is not 1. 0 divided by 0 is not 0. We say that 0 divided by 0, 0 over 0 is indeterminate form. But we can say that 0 divides 0. And it's only 0 that actually divides itself. Now we state the last property of divisibility, and it's called the comparison property. The last divisibility property is known as the comparison property. And it states that if D and N are positive integers and D divides N. Again, D is a positive integer, N is a positive integer, and D divides N, then the conclusion of the comparison property is that D is less than equal to N. We are able to compare the integers D and N. The integer N is smaller than N, or the integer D is smaller than N, or the integer D is exactly equal to N. Or if you read from the right, going to the left, the integer N, the positive integer N is greater than D, or the positive integer N is exactly equal to D. And this will only happen if the integers D and N are positive and D divides N. Again, if D and N are positive integer and D divides N, then the divisor D is less than equal to the integer N. We now prove this divisibility property. We start with the given. We start with the given that D divides N, and we use the definition of divisibility. By definition of divisibility, D divides N means that there exists an integer K. Means there exists an integer K such that the number N is equal to the divisor D multiplied by the integer K. Or N is equal to D multiplied by K. Now, D is a positive integer, N is a positive integer. And the smallest positive integer is, suppose we assign positive integers to K. If K is equal to 1, then D will be exactly equal to N. And this conclusion is true. D is equal to N if K is equal to 1. Now, if the integer K is not equal to 1 but greater than 1, say 2, if K is 2, then you would get N is equal to D2, D times 2, or 2 times D. If K is an integer greater than 1, if K is equal to the integer 1, we have shown that D, the positive integer D, is exactly equal to the positive integer N, which is one of the conclusions in this comparison property. If we take an integer K that is greater than 1, say 2, you get N equals D times 2, but D times 2 is 2 times D. From here, you can say that N is greater than D, or D, from here N is equal to 2D twice of D if K is the integer 2. And you can say that N is greater than D because the value of N is twice the value of D. Or you can say, if you read from right to left, D is less than N. And this will be true, D less than N, if K is 3 or 4 or 5 or any positive integer greater than 1. Similarly, if K is, so we write that down. Again, if the integer k is an integer greater than positive 1, then n is equal to d times k, where k is an integer greater than 1, as in our example earlier where k is equal to 2, n will be equal to d times 2 or 2d. And 2d is greater than d. 2d is the value of n, and n is greater than d because n is twice of d if k is 2. But in general, for an integer k greater than equal to positive 1, the value of n equals dk is greater than d. Or we say d is less than n. Now we consider integers that are, integer k that is less than. Now suppose we assign values of k that are less than positive 1. We check if this is possible to have values of k that are negative. We just want to find out that, we just want to make sure that there exists integer k such that n equals dk. And that d, we conclude that d is less than equal to n if d and n are positive integers. We already know that there is an integer k, 1, such that this is satisfied, n equals dk is satisfied if k is 1, and that would give us n equals d, which is one of the conclusions, d equals n. And we have also shown that for positive integer k greater than positive 1, n will be equal to d times k. N is equal to k times the value of d, which means that n is greater than d, d is a positive integer, or d is less than n. Now we consider values of k less than positive 1, and we check if that is possible. Say if k is equal to negative 1, you would get n equals d times k equals negative 1. And d is a positive integer. If you multiply the positive integer d by negative, that would become negative integer. So negative d is an integer, but negative d is equal to n. And n equals negative d, and negative d is a negative integer. But that will contradict the given that n is a positive integer. So it's not possible to have values of k that are less than the positive integer 1. But it suffices to know that there exists integers k. K is 1, which would give you b equals n, and positive integers greater than 1, which would give you b less than n. Thus, we combine these two results and we conclude that d is less than equal to n if d divides n and d and n are positive integers. we combine the two results we obtain d equals n if the integer k is equal to the positive integer 1. And we obtain the result t less than n if the integer k is an integer greater than positive 1. And we combine these two results. We now conclude that d is less than equal to n, which is the conclusion of the comparison property given or if d divides n and the numbers t and n are positive integers. And this completes the proof of the comparison property. For your exercise, for your practice, please try the following exercises. For your first exercise, you are given that d divides 5 and d divides 3. And you must show that d divides 5a plus 3b for all integers a and b. As we said earlier, 5a plus 3b represents linear combination of 5 and 3. In number 2, the given is d divides a and d divides b. And you will prove that d divides the difference a minus b. A minus b represents actually one of the linear combinations of a and b. Number 3, if a is an element of c, that is a is an integer, it can be negative, 0 or positive, then this implies that the only positive divisor of both a and a plus 1 is 1. And if you have question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison, the channel of learning and leisure. Or you may ask your friends and classmates or neighbors to subscribe to my YouTube channel, Art Kalison, so they may learn as well. Thank you for joining me in my class today in number theory.